Hey guys, and welcome back for another lesson. Today we're looking at differentiation and the gradient function. In this lesson, we're going to get into some of the very advanced differentiation type questions that you'll see on GCSE exams. However, let's get started with the very basics of how we differentiate an equation. If you're given an equation of the form y equals several terms where each of those terms are some multiple of some power of x, you just need to follow these steps. We multiply the coefficient, that's the number in front, of each term by the power of the x variable, and then we subtract 1 from the power. Let me show you what I mean with these two terms. So, to find dy dx, that's the differentiated y equation in terms of x, we took the power of the x and we multiplied it by the coefficient of that x term. And then we subtracted 1 from that power. For the second term, we did the exact same thing. We took the power of the x and we multiplied it by the coefficient of that x term out front. And then we remembered to subtract 1 from that power. Note the dot, dot, dot. We'll do the same thing for all terms of this equation. We call this dy dx because we've differentiated the equation y, which involved the variable x. However, if we were asked to differentiate some function of the form f of x, it's the function f which involves the variable x. Our differentiated function would be called df dx. That's the differentiation of function f in terms of x. Similarly, if we had an equation where v was the subject and we had variables t in the equation, we would differentiate this equation v in terms of t. So dv dt. And note, I just followed these steps here in order to differentiate that. I did 3 multiplied by the coefficient out front, 3 times 2, 6, and I subtracted 1 from the 3, so it's t to the power of 2 now. And I did 2 multiplied by the coefficient out front. 2 times negative 5 is negative 10. And I subtracted 1 from the 2. So that's just t. So generally, when we talk about differentiation, we talk about dy dx, but it could also be of the form df dx, or dv dt, or d of any variable over d of another variable. We could also use the notation that the differentiation of the equation for y is y prime. That's y with a little line up here. Or the differentiation of the f function is f prime of x. Or, for any Transformers fans out there, we could say that the transformation of Optimus in terms of x.
I am Optimus Prime.
Before we move on, I hope these two steps for differentiation are fairly straightforward. We take the power, we multiply it out front, and we subtract 1 from that power. Because differentiation in this way can only happen if you've already got the equation in the correct index format. That is, we've got one variable equal to the sum of various terms where each individual term is some multiple of some power of the other variable. Let me show you what I mean. In this example here, we've got y equal to some fraction. Now that's not going to work when we try to differentiate. We need to write y equal to the sum of several individual x terms, where each of those x terms is some multiple of some power of x. So let's split this big fraction into separate fractions where each of the terms in the numerator is being divided by the denominator. Now you can see that I've got y equal to separate terms in terms of x. However, each of those terms are fractional terms, so let's simplify those fractions. In these fractions, we've got numbers and we've got variables. Now the numbers can be divided, and I can write that simply as the fraction 3 over 2. But the variables, as they have the same base and they're being divided, we can use laws of indices. X to the power of 4 divided by x to the power of 3, the division law tells me to subtract those indices. So that's going to be 3 over 2, x to the power of 4 minus 3, and 4 over 2 times x to the power of 2 minus 3, and 6 over 2 times x to the power of, now if there's no power there, remember that's 1, so this is 1 minus 3. Simplifying that, we get 3 over 2x to the power of 1 plus 2x to the power of negative 1 minus 3 times x to the power of negative 2. Now I've put my powers in blue here so you can clearly see what the powers are. So when I differentiate, you know that we're going to multiply this 1 out front and subtract 1 from this 1. We're going to multiply this negative 1 out front and subtract 1 from this negative 1. And we're going to multiply this negative 2 out front and subtract 1 from this negative 2. Be careful with your positive and negative signs. So 3 over 2 is simply a half. And if I take 1 away from that 1, it becomes 0. Multiplying this 2 by the negative 1 makes it negative, and subtracting 1 from that negative 1 makes it negative 2. Multiplying negative 3 by negative 2 makes that positive 6, and subtracting 1 from this negative 2 makes it negative 3. Now this is my differentiated equation, and I can leave it in this format, however, it's not fully simplified. You should note that x to the power of 0 gives a value of 1. So this would be 1.5 times 1, with no x variable at all. And you should know that negative indices represent fractions. So this is actually negative 2 times 1 over x squared. So this simplifies to become 1.5 minus 2 over x squared plus 6 over x cubed. Here's another example where the equation is not in the correct index format to begin with. At least it's not a fraction. However, y is not equal to the sum of separate x terms where we've got a coefficient which is multiplying by some power of x. I've got brackets here, and these brackets are being squared. That needs to be expanded out. And don't make the mistake of thinking that x minus 4 squared is simply x squared minus 16. We need to write the bracket out twice and expand it out correctly. So expanding those brackets out, I will do x times x, which makes my x squared, and I will do the negative 4 times the negative 4, which makes my positive 16. However, I also need to do x times negative 4 and negative 4 times x. That simplifies by grouping my like terms in the middle here to make negative 8x. And then this bracket needs to be multiplied by the value out front. 5x cubed multiplies by each of these terms, giving me 5x to the power of 5 minus 40x to the power of 4 plus 80x to the power of 3. Note that this is still y. I have not differentiated this equation yet. I've just put it in the correct index format, where y is equal to 3 separate terms, each of those terms being some multiple of some power of x. So I'm ready to differentiate. I can clearly see what my powers are. These are the values that I'm going to multiply out front, and then I'll subtract 1 from them. So dy dx becomes 5 times 5, and then I subtract 1 from the 5. Negative 40 times 4, and then I subtract 1 from the 4. And 80 times 3, and I subtract 1 from the 3. Giving me 25x to the power of 4 minus 160x to the power of 3 plus 240x to the power of 2. Now, hopefully, once we've got our equation in the correct index format, differentiation is getting pretty straightforward. Multiply the power out front, and then subtract 1 from the power. But let's have a look now at why we differentiate. What does differentiation mean? As I mentioned before, today we're looking at differentiation and the gradient function. You should be familiar with the word gradient from when you looked at the equations of lines. Here I've got a line graphed for you, and I'm saying that the equation of this line is y equals mx plus c, where m is the letter that we use to represent the gradient of a line. The gradient of a line is its steepness, and we can work out the steepness using the fraction rise over run. That is, when we move from one point on the line to another point on the line, we look at how far our point has risen up, that is the change in the y value, or we could say delta y or dy, over the change in the x value. How far has that point moved across to the right? We call that the change in x, or delta x, or dx. So using this notation, you should see that the gradient, which is rise over run, could also be written as dy, change in y, over dx. And in this particular example, you should see that the change in y is that it's risen 1, 2, 3, 4, 5 units, and the change in x is that we've moved across to the right 1, 2, 3, 4 units. So 5 over 4 is our gradient, which simplifies to 1.25 as a decimal. But you should remember from the equation of a line that c is the y-intercept. So that's this point here, whatever that may be. And our equation for this particular line is y equals 1.25x plus whatever that c value is. If I want to differentiate this equation for a straight line, let's make really clear that y is in the correct index format. Y equals some multiple of x to some power plus some multiple of x to some power. But let's make those powers clear. This is y equals 1.25x to the power of 1. Remember that when there's no power here, there is a single x that we're multiplying by, so that's x to the power of 1. However, here there is no x at all, so we could say that c is being multiplied by x to the power of 0. Remember, a 0 index means 1, so this is c times 1, which is simply c. But this format is going to help me to differentiate. Take the power, multiply it out front, and subtract 1 from that power. dy dx becomes 1.25 multiplied by the power 1, and subtract 1 from that power, so 1 minus 1. My second term might look confusing, but you'll notice that if x has a power of 0, we'll multiply the 0 out front, and c times 0 becomes 0. Then we'll subtract 1 from that power, but it really doesn't matter what we have in terms of x, because we've got 0 times our answer anyways. So this becomes 1.25 times 1, x to the power of 0 plus 0, or simply 1.25. Notice that the gradient for a straight line is just a number because the gradient is the same along the whole length of the line. The gradient of a curve, however, is different at different points along the curve. Let me show you what the gradient is over here. Here the gradient looks quite steep and it's definitely going downwards. That's a negative gradient. Whereas further along the curve, this gradient is still negative but not quite as steep. Well, this gradient looks perfectly horizontal. And we keep going, and now it's going into the positives and getting more positive. So as you can see for this curve, this positive parabola, we started with a negative gradient, which got less negative and eventually became positive and got more positive. The gradient is increasing as we move across the graph to the right. One important gradient to take note of, which will become important in our gradient questions, is where the gradient is horizontal. Notice on this positive parabola, the gradient is horizontal right here at the very bottom of the curve. Horizontal lines have no rise. It doesn't go up at all, regardless of how far we run. So the gradient here is 0. And when we find a gradient of 0, that will always be either at the maximum or minimum or turning point of a curve. In this case, our gradient is 0 at the very bottom of our curve. That's our minimum point. Now, this is important. You're going to want to write that down. When we work out the gradient function, that is, we differentiate the equation for the curve, the result is a set of calculations which we need to perform to work out the gradient to the curve at some x coordinate along the curve. As we just saw, the gradient to the curve is different at different points. You may or may not be given a graph for these types of questions, but I'm using this graph now to help illustrate what we're talking about. So if you're given an equation like this, y equals negative x squared minus 2x plus 3, and you're asked to work out the gradient function for the curve. We don't need to know what the curve looks like. Let's just differentiate. Take the power, multiply it out front, and subtract 1 from the power. Let's make those powers clear before we can do that. The first term's got a power of 2. The second term doesn't seem to have a power, so that's a power of 1. And the third term doesn't have an x value at all, so that's x to the power of 0. Differentiating, multiplying those powers out front and subtracting 1 from those powers, we end up with negative 2x to the power of 1 minus 2x to the power of 0 plus 0. in an equation where there's a term with no x variable, when we differentiate, that term disappears, it becomes 0. So that simplifies to be simply negative 2x minus 2. So now that we've got the gradient function, what can we do with it? Work out the gradient where x is equal to 1. As we said before, the gradient at different parts along a curve will be different. The gradient here where x is equal to 1 is a negative gradient. I can see that. And I could estimate it by drawing a line on here and see how far I rise, in this case I fall, as I run across. But this would be a lot more accurate if I simply substituted my x value into the gradient function to find out what the gradient is where x is equal to 1. Negative 2 times 1 minus 2. Working that through, that's going to be negative 2 minus 2, which is negative 4. And again, you're not generally given a graph for this, but as we've got a graph over here, you can see that this steep negative line does roughly have a gradient of negative 4. If I run 1 across on this graph, I need to fall down, so negative 4 units to get to another point on the line. As we said before, the gradient for this curve depends on which point on the curve we're looking at. So what about when x is equal to negative 2? That's over here. And as we can see, when x is equal to negative 2, if I were to draw a line which touches the curve just at that point and seems to follow the steepness of the curve at that point, we've got this tangent, which seems to have a positive sloping gradient. But to be absolutely clear about what this gradient is, let's substitute negative 2 into the gradient function, and I end up with negative 2 times negative 2 minus 2. Working that through, we end up with 4 minus 2, which is 2. Notice that the tangent seems to have that gradient of 2. If I run across 1, I need to rise up 2. Rise over run, 2 over 1 is 2. More often, we're asked to find the maximum, minimum, or turning points on a curve. And remember, we find those maximum, minimum, and turning points where the gradient is equal to 0. Now, I can see from my graph where my maximum point is, but we're not always given a graph. So using our differentiated equation, our gradient function, we'll set that gradient function equal to 0 and work out the value of x when the gradient is equal to 0. So rearranging this equation to get x on its own, we work out that x is equal to negative 1. However, this is not the answer to the question. The question asked, what is the maximum point on the curve? A point is a coordinate, an xy coordinate. So while x is equal to negative 1, when the gradient is equal to 0, what's y? For this, we're going to need to use the original equation, which tells us what y is in terms of x. Do not substitute negative 1 into the gradient function because that's just going to give us an answer of 0. So our maximum point is the y value when x is equal to negative 1. Substituting negative 1 in for x, I've got negative 1 squared. Make sure you use brackets when you substitute in, especially when you're substituting a negative value in. Minus 2 times negative 1 plus 3. Working that through, that gives me negative 1 squared makes it positive. Minus 2 times negative 1 makes that plus 2 plus 3, which gives us 4. Again, I can see that on my graph, but I don't always have a graph. So my maximum value for y is 4, and my maximum point is negative 1, 4. You're going to definitely want some examples of this written down. So if you haven't been copying up until now, you may want to hit pause, go back, copy that out, and come back when you're ready to see the other types of differentiation questions that we often see on exams.
There's more to them than meets the eye.
The different types of differentiation questions that we come across are simply when we're asked to differentiate or work out dy dx, or y prime, or df dx, or f prime of x, or any other notation which means to differentiate. But remember, you first need to have the original equation in the correct index form before you can take the power and multiply it by the coefficient out front and then subtract 1 from that power. The next type of differentiation question would be to work out the gradient or slope or steepness of a curve at some given point or x value along the curve. In order to do this, you may first need to differentiate the equation for the curve and then substitute the given x value into the differentiated function. Take care not to substitute this x value into the equation of the curve because that simply gives you the y value, not the gradient of the curve. You might also be asked to maximize or minimize, which simply means to find the maximum or minimum or turning point of a curve. In order to do this, again, you'll need to differentiate the equation for the curve, ensuring that it's first in the correct index form, and then set the differentiated function equal to 0, because the turning points on a curve always have a gradient of 0. Once you set that equal to 0, rearrange that equation to solve for x, but be aware that you were asked to find the maximum or minimum. That's not the x value, that's the value of y at that x value. So you'll then need to substitute that x value into the original function for the curve, not the differentiated function, because that'll just give you an answer of 0 again, into the original function where you've got y equals, and working out your y value, that will be either the maximum or minimum or turning point. Again, make sure you copy this down before we get into some practice. On to the practice exercise now. Here are 4 different types of differentiation questions. For this first one, you just need to find dy dx, that is, differentiate this equation, and note that it's already in the correct index form. Then find the gradient of this curve where x is equal to -3. So using your dy dx, substitute -3 in for x. For question 2, we've got another curve here, and we want to find again the gradient function, dy dx. But then we need to work out where point P is on this curve, given that the gradient at P is equal to -3/2. Make sure you read that carefully. X is not equal to -3/2. It's the gradient that's equal to -3/2. So using the gradient function you worked out in A, set it equal to -3/2 and work out the x value. Now, the question asks us to work out the coordinate of P. That's an xy coordinate. So once you've got the x value, you'll need to use the original function to find the y value and give your answer as a coordinate. For question 3, again, we've got another equation of a curve. And notice what type of curve this is. It's not a quadratic, it's a cubic. Cubics have 2 turning points. Find dy dx, so differentiate this equation and work out the coordinates of these 2 turning points. Remember, the turning points is where the gradient is equal to 0. You'll find the x values for this, and don't forget to then use those x values to find the y values. Finally, question 4. I love these questions, they come up all the time. Here we've got a diagram of a cuboid, and we're going to use V to represent the volume of this cuboid. Look at the given information. The length of the cuboid, as we can see on the diagram, is y. And the width and height of the cuboid, again we see on the diagram, they're both x. We are told some additional information that the length of all edges of this cuboid is 112. Now that's not just x plus y. It's the length of all edges, so all of these lengths, all of these widths, and all of these heights add up to 112 centimeters. From this given information, you need to show that you can work out this equation. That is, the formula for the volume is equal to 28x squared minus 2x cubed. What I love about these questions is you could probably work out this equation on your own, just by the given information. However, since they ask you to show that it's equal to this, they're telling you the answer. So go ahead and work out your own equation for the volume and check to make sure that your equation for the volume is equal to this one. You must show all your working because they've given you the answer here. But even if you couldn't work out your equation for the volume of this cuboid, they gave it to you so you can still do part B. You can still differentiate V in terms of X, and then you can do part C. Find the maximum volume of the cube given your answer to 3 significant figures. Remember, the maximum or minimum or turning point is where the gradient function is equal to 0. So when dv dx equals 0, you'll find your x value, but also make sure you use that x value to find the volume, the maximum volume. Okay, hopefully those explanations has helped you get started. Go ahead and hit pause now, give it a try, and hit play when you're ready to take it up. I hope you had a chance to hit pause, because here come your answers. For question 1, we differentiate. Simply take the power, multiply it out front, and subtract 1 from the power. For part B, the gradient to the curve where x is equal to -3, you've just substituted -3 into the gradient function. For question 2, again, we differentiated, take the power, multiply it out front, and subtract 1 from the power. And part B, when the gradient is equal to -3/2, we simply set our answer from A equal to -3/2. It's a quadratic. I hope you got it equal to 0. It's a difficult quadratic to solve, particularly because of that fraction, so multiplying both sides by 2, including the 0. 0 times 2 is 0 still. I got rid of that fraction. However, it's still quite a difficult quadratic because we've got these big numbers, particularly the big number in front of the x squared term. So find the highest common factor, which is 3, and divide both sides by 3. It's still a difficult quadratic to solve. You might need to split the middle term, or you might realize that 4x squared is the result of doing 2x times 2x, and the 4x in the middle is the result of adding 2x plus 2x. You can complete the square and see that this is 2x plus 1 squared. Now, solving for x, there's only one solution for x because it's going to be the same solution for both of those brackets. X is a -1/2, which means point P must be where x is equal to -1/2, and y, well, I use the original equation for y for this, y is equal to 2x cubed plus 3x squared plus 2, where x is equal to -1/2. So that works through to be 2.5. P is the coordinate -0.5, comma 2.5. For question 3, we can differentiate to find dy dx. Take the power, multiply it out front, and subtract 1 from the power. We can work out the coordinate of the two turning points because the turning points are where dy dx is equal to 0. So set our answer from part A equal to 0, and you've got a quadratic that you need to solve. Hopefully you see it's an easy quadratic. There's a common factor. I divided both terms by 3x. I have two solutions to this quadratic. One of them is where 3x is equal to 0, and the other is where x plus 4 is equal to 0. If 3x equals 0, x must be 0. If x plus 4 equals 0, x must be -4. Remember, we're looking for the coordinates of the turning points, not just the x values. So I've got 0 comma something and -4 comma something. To find our y coordinates, substitute those x values into the original equation for y. Y equals x cubed plus 6x squared plus 5, and where x is equal to 0, oops, that showed up wrong. It should be 0 to the power of 3 plus 6 times 0 squared plus 5, which works out to be 0 plus 0 plus 5. So when x is equal to 0, y is equal to 5. When x is equal to -4, substitute -4 into that original equation for y, and y is equal to -4 cubed plus 6 times -4 squared plus 5. And that works through to give y is equal to 37. So we've got the coordinate -4, 37. For our last question now, hopefully you managed to show that v is equal to 28x squared minus 2x cubed. But even if you can't, you've got the formula there for v so you can differentiate and still find the maximum value of the cube. But let me talk you through A first. You're given the information that the total of all edges is 112. So let's write that equation. If I add up all the edges, that'll be adding up the 4x edges on this side, the 4x edges on that side, and the 4y edges along the front and back of this rectangular prism. That's equal to 112. That simplifies to be 8x plus 4y equals 112. And I can rearrange that to make y the subject and y is equal to 28 minus 2x. Now you might be wondering why I rearranged that. Look at the formula for the volume that we need to write. That volume has no y's in it, just x's. So when I work out the volume of this cuboid and I do length times width times height, which is x times y, I don't want any y's in this formula. So I'll replace that y with this expression in x that I've just worked out from the given information. If y is equal to 28 minus 2x, our volume formula can be written as x squared, that's x, times 28 minus 2x, which multiplies through to be 28x squared minus 2x cubed. Exactly the same formula they asked me to prove that I could find. And I did it on my own, showing all stages of my working. Remember, I'm not going to get any marks for simply copying down their answer. I need to show how they got it. So for part B, since we already have the volume formula, we just need to differentiate it. It's in the correct index format. I've got a power of x, which I can multiply out front and subtract 1 from that power. So dv dx is 56x minus 6x squared. Now that I've got dv dx, let's look at part C and find the maximum volume of the cube. Remember, maximums, minimums, and turning points happen when the gradient is equal to 0. So dv dx is equal to 0 when 56x minus 6x squared is equal to 0. Now this is a quadratic we're going to need to solve, but again you can see it's a fairly simple quadratic because there is a common factor. We can factor out of both terms. Both terms can be divided by 2x, and now I've got two solutions. 2x times 28 minus 3x will be equal to 0 when either 2x is equal to 0 or 28 minus 3x is equal to 0. So my two solutions for x are when x is equal to 0 or when x is equal to 9 1/3 or simply 28 over 3. But which of these x values represents the x value where we get a maximum volume? Now, logically thinking, surely some of you are saying, how could we possibly have a maximum volume when x is equal to 0? Surely the volume of the cuboid when x is equal to 0 would be 0. And you're right. But let's look at this another way as well. Check out the formula for the volume of a cuboid. What shape would that curve have if we were to graph it? It's got an x squared term and it's got a x cubed term. It's a cubic. More importantly, it's got a negative x cubed term, so it's a negative cubic. Starts high and ends low. And I've got two turning points. I found the x values at these two turning points. They're 0 and 9 1/3. And the first turning point is a minimum, while the second turning point is a maximum. That is over here where the gradient's equal to 0. That's the lowest point on the curve for this part of the curve. We could call that a local minimum. And this point over here is the highest point on this part of curve. We could call that the local maximum. And if we look at our x coordinates in order, the first x coordinate, the lowest x coordinate, is 0. So where x is equal to 0, that's going to be our minimum point. Where x is equal to 9 1/3, that will be our maximum point. But we still need to work out what that maximum is. So when x is equal to 9 1/3, substitute that into the volume formula to work out what the volume is. Three significant figures, that's 813 centimeters cubed. Now, how did that go for you? I know we started quite simple and we got to the difficult ones in the end. This is definitely going to need a lot of practice to master, but hopefully it gave you a good start. Please leave me a comment down in the comment section if you had any questions or doubts. Otherwise, keep practicing and I'll see you soon.